everybody. Let's start with the next two talks. The first one is Will Handley from the University of Cambridge, talking on GPU-accelerated nested sampling.
Many thanks. Okay, many thanks for sticking it out also to the end of the conference, particularly after the conference dinner. I expect at this meeting most people will know what GPU means, but I also anticipate most people probably don't know what nested sampling means. So I'm going to probably spend a bit of time going through that and guiding you to some of the resources we've been creating to help people with this. But we'll start by, so I am a cosmologist slash astrostatistician. So I'm somebody that works in astronomy and thinks about the kind of statistics problems that astronomers solve. So to give you a flavor for the kind of thing that we try to solve, here is a fun one. Gravitational waves are caused by merging black holes or merging neutron stars or other things, and they're generally ripples in space-time that propagate across the universe for about 1 billion to 10 billion years, depending on which ones you're looking at. You hear these by measuring very small changes in the distances of mirrors that are separated 40 kilometers apart in LIGO Livingston and LIGO Hanford in America. And when you hear them, the time delay allows you to tell you where they are. So you can basically listen to the ripples in space-time and say, that merger event came from that bit of the sky. The fun thing that we want to do is to say that bit came from that bit of the sky, so everything else, go and look over there immediately in case you can also see the explosion that caused that gravitational wave. So you get the gravitational wave detectors that are hearing things, and you hear the in-spiral coming in, and you basically say, you have an alert that triggers, and all the telescopes go and swing to cover that patch of sky. This is phrased as a real-time Bayesian inference problem, where basically what you try to do is to construct the posterior distribution over the full space of the event, of which the critical bit is the sky location. So this is therefore a parameter estimation problem on a space that looks something like S2 cross S2 cross S1 cross S1 cross R to the 10. This kind of thing. So it's a non-trivial geometry in terms of the parameter space you're observing, and you are trying to do this really fast. Ideally, you want to do it in seconds in order to get the telescopes to capture the explosion going off as they merge. It is very hard to do that, and at the moment, the only solution we have to that is to build machine learning classification triggers that kind of say, this is a probable event, everybody drop what you're doing and swing the telescope to look at this bit of sky. And ideally, you'd have the full posterior such that you could patch it saying, well, from here, let's go back, from here, although I know that the event is here in the sky, it could be here. So we should probably put something at that bit there, because there's a possibility in terms of how this posterior is constructed that because we've only got this level of information at this moment of time, we should probably cover the maybe 5% possibility that it's in that bit of the sky as well. We can't do that with machine learning, and it would be nice to be able to build full posterior samples of this to inform telescope follow-up. So as I kind of intimated, this is a hard problem on a complicated space that's usually tens to hundreds of parameters, and we have real multimodality in the posteriors. You can't sort of statistically mumble it away by saying more data. This is multimodal, and the multimodality represents your knowledge of what's happening. So you want to cover all the options. And these things are not cheap. Like on a CPU, each likelihood call can take sort of a few fractions of a second, and that means that these things typically will take many, many hours to run these through. So you want to bring hours down to seconds is the kind of plan, and that's the kind of thing that GPUs might be able to do. That's the seed of this talk. Right, so within Bayesian inference, just for notation, we talk about posterior and parameter estimation, where you have some scientific model and some data that you've observed, and you want to say, what does that data tell you about the parameters of the model? And Andrew was saying yesterday, the posterior is the thing that captures that properly. You don't really want sort of credibility regions, confidences, you want an actual representation of the posterior, which is represented, if you're using MCMC, via samples. This is a problem where you might turn to tools. Okay, who here has used STAN? Who here has used MC? Who here has used nested sampling? There's a couple of astronomers here and there, so it's not nobody, but it's still there. Okay, model comparison is the other stage of Bayesian inference that people like to argue about priors a little bit more there. But fundamentally, it tries to use Bayes' theorem to solve the second stage, which is, okay, I've got given a model, I can tell you what its parameters are likely to be, but as a scientist, I'm very interested in knowing which model is the most likely. And in the context of gravitational wave follow-up, that would be, I have an event coming, and I want to prioritize how many telescopes I tell them to break what they're currently doing to go look at that. So I want to know if this is a binary black hole merger, because there shouldn't be any optical counterpart to that, or I want to know if this is a neutron star merger, because there definitely will be, because we have seen one. This is sorry, that's the other hidden bit. We have achieved this procedure here of follow-up once, partly because we got lucky, because it was a very long in spiral, and we were able to. We had a lucky coincidence of things where we had a very good localization. The telephone number for that event, which was GW 170817. We watched about an Earth's worth of gold being created in the merging neutron star event. So if you're wearing any gold jewelry, those came from merging neutron stars, and we know that now because we saw it happen. Right. In terms of other tools, usual MCMC will give you posterior events, posterior samples, and ensemble methods can be better at getting multimodality, but in general, very few of these things, apart from sequential Monte Carlo, will target getting this crucial factor in Bayesian model comparison. So here, if your model is this neutron star, or black hole, or your model in cosmology might be, is the universe made of dark matter and dark energy? Does dark energy evolve over time, or is it constant? And what is the most consistent thing with the data that we've seen so far? Model comparison forms the core tool for how we do this in astrophysics. And model comparison is hard. SMC is one of the tools on the market that can do it, and nested sampling is another. And that's what I'm now going to hopefully introduce to you. So here's some nice pictures. Here's the picture you should have in mind for a normal Metropolis-Hastings algorithm. Here, these are the contours of some initially a priori unknown distribution. You pick a point in the middle, and you run a random walk where basically you accept or reject based on the ratio of how much you've moved uphill in this distribution. And over time, you build up posterior samples, and those samples from that distribution constitute a representation of the posterior that captures all of its infelicities like bending degeneracies or multimodality or things like that. The trouble with a chain-based approach is that it can get stuck in local minima. You have theorems that guarantee if you run it for the Hubble time, it will find them all, but we don't have the Hubble time, and often your usual things will terminate early thinking that they've got to that stage. Nested sampling does this in a different way, and this will seem a lot like sequential Monte Carlo because it is. So if you know what SMC is, I'm now going to present to you something that is pretty much SMC, and I'll come back to how it's different in a second. You draw samples across the whole space, initially from the prior or from the range that you're interested in. You then evaluate the likelihood on those samples and throw away the lowest fraction. In this case, let's throw away the lowest half, and that way you get to that point there. So you've got now the blue samples, which are the ones that were half higher, and then the grey samples that were lower. And then after you've thrown away half of them, you repopulate within that hard contour. That's the nested bit of nested sampling. You are kind of nesting these contours inside. So you start by drawing samples from the prior, you throw away the lower half, and then replace them with points that are higher than the midpoint that you've just thrown away from, where that midpoint is defined by the samples. You repeat that process and get an evolving set of live points that sort of hopefully contract around the peaks. If you're awake, there should be a question that springs to mind, which I didn't tell you how to generate those new live points. I just said generate some new live points that are higher than that contour. And John Skilling, when he proposed nested sampling, left that up to users to do, basically, to find some way of doing it. For now, let's assume you've got a process of doing it, and we'll come back to how we will actually do it in practice. But to summarize these kind of two approaches, the MCMC or Metropolis-Hastings approach has a single walker, which is basically extremely good if it's well-tuned at generating posterior samples. You can't really get better than that unless you actually have a real generator. A well-tuned Metropolis-Hastings will win, but well-tuned means often you need to know the answer going in, which in the gravitational waves context just isn't true. You don't know the answer, it's a new thing that you've never seen before, and you have seconds to find it. So Nested sampling has this ensemble approach, like MC or other things, where it kind of evolve, or particle filters or things like, where it evolves a set of points such that they scan from the prior to the peak of the likelihood going through the posterior at one moment in time. It doesn't actually target the posterior, it scans from tail to tip. And it really, if I'm being technical, it's not a posterior sampler, it's a partition function calculator. So just to kind of summarize that in words, so you can see that here, you start with n random samples of the space, you throw away the outermost sample, or the outermost half, and replace them with a random one at a higher value of the likelihood. And the lie points therefore steadily contract around that peak. Now, the magic of nested sampling is that if you've done any Monte Carlo integration before, if you know the size of this box, which you do because it's the prior, so we'll call that box size 1, and you want to know what the volume of this region is here, you can estimate the volume of that region by saying it is about half, because I threw away half of the points from the box. If you want to estimate the volume of this region here, it will be about a quarter, because I've gone half again, and now it will be about an eighth. That idea of measuring volumes by counting is very normal in the context of Monte Carlo integration, and what nested sampling does is to bootstrap those together such that you have this controlled measurement of volume that never mentioned dimension or topology. So you don't need to know what these contours look like to count things to measure what their volume is. Now, of course, it's not exactly half, it's a half plus or minus a bit, but that's a first year stats problem to work that out, and you can therefore track those errors through and work out how these things evolve. And that is fundamentally what you do, because once you've got volumes, this idea here of computing the volume under the curve, or the marginal likelihood, or the Bayesian evidence, the integral of the likelihood times the prior over the whole parameter space, now just becomes something where you can now calculate this. You've now got something where you have the integral over the whole space can be summed as basically over these nested shells, where we estimate these nested shells as an exponentially contracting inwards region. Half, quarter, eighth. It's all more carefully done than this, but this is the heuristic kind of way of thinking about it. Any thoughts or comments at this point? Who here has seen a talk about this in any way at any point? There's a few astronomers that have seen some of these slides. If you've noticed, some of the previous slides have changed because I'm now running blackjacks to make these slides in order to do it. So, okay. Any questions? Yes.
The prior would have to be uniform for you to be able to get the volume measured.
So the key core bit, so when I say yes, okay, that statement is true, but then if you transform a uniform prior, you can get any prior you like. So when people talk about nested sampling, they always refer to the uniform prior because they've implicitly done that transformation in the back of their minds. I can talk later about why that was actually very damaging as a way to phrase things, because the core nested sampling algorithm is draw a sample from the prior subject to a hard likelihood constraint. So at the end of this, you actually don't have posterior samples. What you have is a set of samples that steadily compress around the peak or peaks of the distribution. This is quite fun, because it's basically, it's this kind of scale invariant distribution that has this logarithmic behavior with volume, where sort of here, you've got the initial set of points that are sampled from the prior, you've kind of concentrated them around here, and if you zoom in on that, you get this, where you watch them continually concentrate in here. And it's basically the most equitable way to draw samples that cover both the prior and the likelihood peak and the posterior. If you wanted to cover all of those things at once, this is the distribution that does that. Now, the reason why you'd want to do that is because one of the things nested sampling is totally wasted in cosmology and astrophysics for is that it's also a partition function calculator. So material scientists and chemists use this to compute heat capacities and internal energies, because what nested sampling gives you is not just the evidence or the marginal likelihood, it gives you the marginal likelihood as a function of temperature. This kind of L, if you can imagine taking your likelihood times your prior and raising it to some temperature beta or inverse temperature beta, it actually gives you samples from all of these at any beta you like. From beta is 0 to beta equals 1, and the evidence at any beta you like, up until 1, because that's when you stopped it. So people use this to do things like find new kinds of ice, in theory, because if you open any statistical mechanics textbook, the first page usually says the partition function is the single most important quantity in statistical mechanics. It's such a shame that we can't compute it numerically. nested sampling is a numerical partition function calculator. Right, so that's nested sampling, something that is used widely in astronomy, particle physics, material science and chemistry to basically do a lot of physical problems. So it's a general purpose tool for evaluating both posterior samples and marginal likelihoods or Bayesian evidences. So you can perform both steps of the chain in Bayesian inference using nested sampling. GPUs. So again, I'm going to, hopefully this crowd, I don't need to actually explain what a GPU is, but I will draw people's attention to GPUs confer two advantages and they are completely separate, okay? The first advantage usually comes from, or not GPUs, but in general, when people use GPUs, it usually comes from using the JAX or PyTorch ecosystem. So JAX or PyTorch allow you to use gradients, okay? They allow you to compute gradients automatically, and that is what has enabled the machine learning revolution of modern optimization. Before these tools, if you are old enough, you will remember tools like Tapenade or other source code translation softwares. One of the reasons why Stan is so phenomenally successful is because in a world that is before automatic differentiation, it was able to basically say, we can do the gradients for you, you just need to write in our probabilistic programming language. And that's what enabled it to do HMC at scale, was because it said, you don't need to worry about gradients because Stan will compute the gradients for you. Now, we don't need Stan to do this for us because JAX and PyTorch do that, which opens up the kinds of problems you can solve much more widely. This is hugely important, and many people will, and because GPUs accelerate these, many people will think that the reason why GPUs are great is because of gradients. But there's actually two ways that GPUs are great. The first is it allows you to do gradients and JAX and PyTorch. The other bit is that they are just massively parallelizable anyway. Okay, so those two things are separate. So you can get algorithms on a GPU that, in probabilistic inference, that do incredible things without gradients. And if anybody's wondering this, nested sampling currently doesn't use gradients. No gradient information at all. And I've burnt several years of different PhD students' time trying to fix that. So GPUs are good at doing a very specific kind of parallelization, which is where you have basically thousands of cores versus tens on a CPU, providing you write within a code that can use them. And nowadays, JAX and PyTorch make that possible. The more important and pertinent thing for all scientists, particularly in the kind of physical science that I do, is that if you use high-performance computing, so if you use supercomputers to run things, all of the future HPC is going to be GPU. There are going to be very few CPU computers built because of the basically unending thirst of AI that we need. So all of the modern HPC machines that are planned and will be built will all be GPU. And therefore, if you want your science to remain in step with the computational improvements, we need to port things to GPU. I often get quite frustrated when I watch people give talks on how great their code is on a GPU, because it's not an apples to apples comparison, in that, as a rule, there we go, get the button right, although you can get, you say, I took this algorithm and I put it on a GPU and it's 10,000 times faster. That's something that people will often say. And they're not wrong as stated. In wall time, it will do it 10,000 times faster. And there are some times when all you care about is that. Gravitational wave follow-up is very much one of those. It's where it's a real-time thing. I need this to happen now. I don't care how much it actually costs me in terms of pence to run that GPU. I need the answer in seconds, not minutes. But if you're thinking about doing analysis at scale, you should always bear in mind that GPUs are 40 times more expensive to rent. That's just at the book value that we pay for on Dirac. And GPUs are 100 times rarer in HPC allocations. So they're both less easy to find and more expensive. So when someone says 10,000 times faster, you should always divide that number by about 100, because that's how much it would cost to do it on a CPU for the same sort of energy that would both build and run. And why Blackjacks? So Blackjacks is one of these languages that runs all this, so that allows you to use GPUs. Why did we choose it? It's because at the moment, nested sampling sits in a scattered and rather fractious ecosystem. There's been a sociological convention of people writing a paper that is nested sampler's name, : the best nested sampler ever. Well, that might be Multinest or Polychord or Dynasty or Ultranest or Nautilus or NestAI. We're trying to break that trend by creating a community code that nobody owns, but we all can contribute to, because Blackjacks already exists as a tool for doing this. It's also good because Blackjacks already implements things like HMC, or when you implement something like slice sampling for nested sampling, it's then there for other people to use in other algorithms. So that composable algorithm is very useful. And of course, Blackjacks is proper first-in-class. It's as good as Google gets in terms of producing these things. If anybody has used MC, the author of MC, who's called Dan Foreman-Mackey, writes Blackjacks for Google, or writes Jacks for Google. So Jacks has kind of got a good it's in good hands. And I'll also point out that ensemble methods like MC, or like SMC, or like nested sampling are better suited for doing GPUs because you can parallelize over particles. So whereas normally, with an HMC approach, you can run multiple chains, but because your usual amount of time is burning things in, there's not much point in running millions of chains. Even though you possibly could on an A100, you might as well only run 8, and then you're never really using the full power of a GPU. Because most scientific problems are not like the deep learning models. GPU memory is rarely limiting, and therefore there's a lot of times where we've been coming into people's codes and saying, if you change this, you do realize you will make your code 1,000 times faster because you will actually use the whole GPU. Okay, and then in terms of our kernel, so as I said, within nested sampling, there's lots of different ways of achieving given this setup at any moment in time. How have I done that? Given this setup, where you have these live points, and you want to throw away the lower half and repopulate with points at higher likelihood, the task of how you generate new live points can be done by a variety of ways. If you are in 2008 and you reach into your box of numerical tools, you'll pull out non-convex hull samplers, and that gives you multi-nest ellipsoidal decomposition. If you do it in 2020, you reach into your tools and you pull out normalizing flows, and that gives you Nautilus on SAI. Many of the other tools end up using some variant on slice sampling, and we are still exploring the theoretical links between nested sampling and slice sampling because they do fit extremely well together. If you haven't used slice sampling, the paper by Radford Neal is very good. Okay. Here's some fun numbers because this is what you do in GPUs. We took to be clear, the full answer that we want to get in seconds in Bilby and Dynasty takes 2 hours on 400 CPUs. That's what the full MCMC algorithm takes to process the gravitational wave data at full resolution with a full likelihood running a full sort of MCMC sort of fit, be that HMC or be that nested sampling or something else. Other GPU methods have shown that you can do this in 742 seconds, which is the kind of the GPU MCMC version of this, and GPU nested sampling is competitive with this. It's a similar speed to that. So you get that speed up of going from literally 400 times 2 hours, so a very, very long time, as fast as you can, to now coming into seconds. And whilst this wouldn't have done for the electromagnetic counterpart event, we're looking for ways to go further and speed up things even more. And this will do for other kinds of events. There are things that we might have seen if we'd had this algorithm a few years ago. And these do tend to agree. If you then take it out of gravitational waves and go to the CMB, we get to a different mode where you can take something that would take an hour on a CPU to 12 seconds. Again, this kind of silly speed up is very impressive, but you should always divide that number by 3, by 100, and only get 3 into its real speed. The cosmic shear is an interesting case study. It's agreed that full Euclid, which is our new sort of big survey satellite, will take 8 months on 48 CPUs, which is just not an option. You just can't do that. That takes too long. The existing work that Alessio and Davide Perez built takes 2 days on 12 A100s. We made 2 fixes. We first of all switched to Blackjacks and found that was slightly faster, and also fixed their likelihood to find there was a big inefficiency in how they were using it. And that these 2 days on 12 has come down to 4.5 hours on 1. So this kind of thing here where you speed things up, so I'm not saying that this is better than nuts, because when you do an apples to apples on this, it's Blackjacks and nuts will be very similar. So Blackjacks and nested sampling will be very similar, but this 2 days on 12 to 4.5 hours on 1 came with the other significant thing that I want to say, which is going to change everybody's lives. Out of interest, who here uses LLMs to write code? Who here uses them to write grants? Who here uses them to write job applications? Who here uses them to write emails? And to answer emails. Okay, good. So people are doing that. So this is a room where people are quite awake to this. Who here's used Claude Code? Okay, if you haven't used Claude Code, go look that up. That is the next stage. Claude Code CLI is the agentic systems that are now coming online, and Gemini's one came online 2 days ago. So, the real AI revolution, in my view, is not using AI for analysis. AI for analysis is cool. Like, you can do some really interesting, fun things with generative models that we've seen this week. But that is the 20% hard bit. Where AI is going to change everything is the 80% boring bit. Many companies will come and give AI their hardest problem, and AI will fail spectacularly to solve their hardest problem because it's their hardest problem. It may not be solvable. If it's not solved by humans after you having thought about it for a very long time, AI is not going to do it. AI is not good at that. It's good at the rest of the stuff, where some of it is very, we're very happy to give away. So things like filling out forms or Excel spreadsheets, checking for errors in papers, so checking for things where that, or summarizing somebody else's paper to say, is it worth my reading it? That's very good. Things where it gets more controversial, things like grading, or things like that. If you want to think about how you might assess students in a world where coursework is being done by generative AI, one way to do that would be to use generative AI to write an exam on their coursework that they take in an exam hall, because that's the way of making sure they've understood their work. But that's 5 years away. I don't think people are going to accept that for a while. The point here is that we use these tools to do that conversion from legacy codes to JAX. And if you're not using these tools to do that, it means that you're not using their full power yet, because modern agentic systems really can, when steered correctly, turn something that took humans many decades to write, can move it into weeks for you to turn that into a new code. And from that, you get these thousands of factor speed up. So if you are using these tools, I reckon you've got about 18 months of advantage over the rest of the scientific community before everybody else wakes up to it. All right, if you're interested in further resource, here's the workshop that I gave a few weeks ago, written by AI. Here is the, and it's very good, much better than anything I could write. Here is here's how you install it. We want it to be merged into the Blackjack's main branch. It's currently on this pull request being reviewed, but if you want to use it now early, you just can pip install it from the GitHub. And if you want review papers, these 2 review papers on nested sampling are very good. And John Skilling's ineffable original paper. It's always worth a read. And here, this is the one that will show you how to run it in relatively short time. So I recommend going to this workshop, this link here. All of my talks are at this link, and you should be able to get that link from there. Oh, and by the way, of course, also, this Beamer presentation was written with Claude Code this morning. So if you've ever written a Beamer presentation, you know you have to be a certain kind of masochist to do that, but Claude can do it in minutes rather than days. Right. So just to summarize, nested sampling very widely used across a number of physical applications, but there has not been until now a GPU native version of this. In terms of this workshop, where you might want to insert an MCMC, nested sampling can now sort of be put in there and often do it much better because it will be able to use all of the clever AI sort of forward models that you've written and all of the kind of other sort of JAXy things. And again, just if you remember nothing else from this talk, Claude Code. That's the thing that you should be using now, okay? And I think, yeah, if you're not writing codes on GPUs because it's hard, you should be because GPUs is the future of how we're going to be running hardware. And if it's hard, you should be using the current AI tools to help you write those things. Many thanks.
A little bit of time for questions. Yes, Andrew.
Two things. One, there are massively parallel HMC algorithms, so you could look at the stuff that Matt Hoffman has been.
So I am very interested in Matt's work. It's something that we are pursuing quite carefully, both in terms of how it interacts with nested sampling and because, as you say, it does work. I still haven't quite got my head around them. So if you're around, I'd love to chat more about them.
I don't know if I understand it so well. You can. I think that one of the principles is that these algorithms themselves are smoothly moving from some starting point to something else. And so that they can have properties, so when they're not all there, so that the model will say, well, I'm warming up and doing nothing, and then when I'm done warming up, I take, well, you're getting somewhere along the way. Okay. The other thing is, I think you might consider comparing your models using predictive model averaging rather than that integral. I don't know enough about your model, but when you compute this marginal likelihood thing, in models in social science, it will depend on aspects of the prior distribution that we typically are assigning arbitrarily. And it might be different in your world, but we found that predictive model averaging actually can work much better than the so-called evidence.
Yeah. So I agree that the evidence is sensitive to bad priors, as any Bayesian analysis is, but it's slightly more sensitive to it than other bits of the Bayesian chain. Here, our prior is quite clear. It could come from anywhere on the sky. It's a uniform prior. So that's often the kind of things that go here. But you do also in cosmology get people writing endless chains of papers that's really just arguing about a really weird prior that we put on things.
Well, you can also use predictive model averaging even in the case where you do have a good prior, and I'm not clear that it would. It could just save you some computational effort. It might work just as well.
So this is where you kind of have effectively a choice parameter that picks a model within that.
I would say that you, instead of computing this marginal likelihood or in addition, you compute. You would find the mixture of models that minimizes the predictive error.
But if that mixture of models is doing a Bayesian average, it presumably has some prior dependency in it there.
It's called stacking, but the idea is that it's not, you're not actually putting a probability in the models. You're just getting the most efficient predictive average.
And the principle is that if you have multiple models that share the same silly prior, that silly prior cancels out between the two.
No, the prior has nothing to do with it. You're using, I won't waste everybody's time.
One more quick question, perhaps? Yes, please.
So you must be making some assumptions of smoothness when you do the nested SAM, and some assumptions about the. If you go back to the. There's an assumption about the size of those peaks that you're going to catch them. So the one in the top corner, if you sample very sparsely, you will not see that. And your nested sampling will just throw that out.
And you are sensitive to basically catching the basin of attraction of it, basically. There are very few numerical algorithms for which that is not true. I agree, you might, in some cases, get some guarantee because you know the answer going in. But for a problem applied to this, we kind of almost treat it as a prior that that kind of a solution is never going to be captured by any numerical MCMC or otherwise. But yes, I agree. The kind of a flagpole in the ocean would never be found. It's just too narrow a peak amongst.
Yeah, you can never find a delta function.
Yeah.
But you could find a little Gaussian bump, and the size, the sort of variance on that Gaussian bump, you should be able to estimate, given the spread of numbers, what size you're missing.
And the fact that you've got sort of this, the same thing that allows you to estimate volumes would give you at least some kind of statement on, we should have found this with a certain level of probability, and things smaller than this will have been missed. You could say that, certainly. So there's a level at which you could do that, but there's no smoothness really in nested sampling. Because the core thing has a hard likelihood constraint, it works quite well on very non-smooth problems. But I agree, volumes of peaks, it will miss, and it can tell you what size of volume of peak it might have missed by this point.
Okay, let's thank the speaker again.